Electric flux. Let us consider an electric field E passes through an area of cross section ds and let the area makes an angle theta with the direction of the electric field. In order to explain the electric flux, what I'm going to do, I'm going to use this information to draw a figure. So here is my figure where you can see that this is my area and the direction of this area is ds, and let the electric field, or I should say a uniform electric field, passes through this area and the direction of the electric field is in this direction and the magnitude is E. Let's consider that area vector ds is making an angle of theta degree with the direction of the uniform electric field. Then the electric flux is defined as phi E is equal to vector E dot vector ds. So basically the electric flux is the dot product of electric field and the area vector. If we simplify further, we will get phi E is equal to E ds cosine theta. So basically, as you can see, this is my electric flux. So based on the value of cosine theta, we can have the different value for the electric flux. So let's consider the different cases. So first case is case 1. When theta is equal to 0 degree, then cosine theta is equal to cosine 0, and that is equal to 1. So let's substitute the value of cosine theta in this equation for the electric flux, and if we do that, we will write phi E is equal to E ds cosine 0, and we know that cosine 0 is equal to 1 from here. So we will write E ds times 1, and E ds times 1 is E ds. So our electric flux phi E is E ds. Our second case is when theta is equal to 90 degree, cosine theta is equal to cosine 90, and we know that cosine 90 is equal to 0. Now let's substitute the value of cosine 90 in the electric flux, and if we do that, we will write phi E is equal to E ds cosine 90, and we know that cosine 90 is 0. So we'll write that is equal to E ds times 0, and anything times 0 is 0. So we will get phi E is equal to 0. So basically the magnitude of the electric flux is 0 when the direction between the area vector and the uniform electric field is 90 degree. Or I should say when the electric field and the area vector are perpendicular to each other. Now let's consider our last case, case 3, when theta is equal to 180 degree, which simply means cosine theta is equal to cosine 180, and that is equal to -1 because cosine 180 is equal to -1. Now let's substitute this value in this equation to get the electric flux, and we will write phi E is equal to E ds cosine 180 degree, and we know that cosine 180 degree is -1 from here. So we will write that is equal to E ds times -1, and we know that E ds times -1 is negative E ds. So basically the magnitude of the electric flux is equal to minus E times ds when the direction between the area vector and the uniform electric field is 180 degree. And this is how we will define the electric flux.